okay, after we put all these pieces together, right, we're doing each of these epsilons. I hope everybody see how for each epsilon, we're saying what's true at the beginning of the epsilon and what needs to be true at the end of the epsilon, and we've solved each epsilon, right? So now we have to put all the pieces together to make sure that that together we solve the problem, all right? And that's the loop invariant religion. And so in order to do that, I want to do the loop invariant religion again. In fact, I don't think I've ever done it with you, but you've watched it, right? So let's see here. View pointers, code. Here, recap. I think this recap is good, all right? So these are the steps that you need to do, right? And I've had people during tests say to me, I don't know how to solve the problem. And I would say to them, well, do you know the pre and post condition? Yes. Do you have a good loop invariant? Yes. Do you have a good measure of progress? Yes. Have you defined the step of what you do? Yes. Do I know what your exit condition is? Yes. Right? When you take this step, if you know the loop invariant is true and the exit condition is not true and you take this step, do you maintain the loop invariant? Yes, right? If the loop invariant is true and the exit condition is not, and you take a step, do you make progress? Yes, right? Can I establish the loop invariant? Yes, right? Do I make sure that the measure of progress will assure that I exit? Yes. From the exit condition and the loop invariant, do I get the post condition? Yes. And then they'll say, okay, great. And they'll say, I still don't know how to solve the problem. And I'll say, well, that's where the religion comes in, right? That's where you have to believe, all right? And so for once, what I want is during the test, you don't convince yourself of this religion, right? I'm going to try to convince you of this religion before the test so that once and for all, you have it in your soul, and then you never have to do it again. You don't have to do it during the test, because during the test, if you start doing it, you'll panic and drown. All right? So let's prove my religion. I always like a religion that you can prove, right? Let's prove it. Here are the various pictures that you have to do for your test, right? And I'm going to prove to you that if you do all of these pictures, then you'll have an algorithm. All right? So let's do it. First, I'm going to say I prove that if we start from a precondition is true and I take the initial step, I can establish the loop invariant, right? And I prove that if the loop invariant is true and I'm not exiting, then I can maintain the loop invariant. And then everybody agree that that tells us that we maintain the loop invariant as long as we don't exit, right? I should put up here a not exit thing. Everybody understand that? That's just some sort of induction, right? You can establish the loop invariant, and as long as the loop invariant is true, you can maintain the loop invariant. So the loop invariant will always be true until you have to exit. All right? Do you agree with that, everybody? Agreed, right? This is the big part of the religion, right? This is the induction part. All right, the next part, here I did have it up here, right? The loop invariant's true as long as you don't exit. That's what we should have had from the last page, right? All right, so what does this picture say? This says as long as the loop invariant's true, you know how to take a step. That means you won't, what does this mean? This means you can always take a step and you won't crash, right? Well, if we prove that the loop invariant's always true until we exit the loop, and we prove we can always take the step of the loop as long as the loop invariant is true, then together that tells us that we can always take a step. Would everybody agree with that?
Right.
This means your loop doesn't crash by doing something you're not allowed to do. right? All right. This says if you're always allowed to take a step, and this says whenever you take a step, you make some progress, then together, that tells me that you make progress, right? That you're always making progress. In this case, as long as you're in the loop, you're moving outwards from the center. All right? So now what do we say? Well, this picture here says when you at the precondition, when you start, your measure of progress isn't infinite. And this says that you always make some progress. Then eventually your progress will get to 0. Now, in our case, we kind of turned it around. We started that we initially were at 0, and we kept having our progress go up. So eventually we'll get to a quarter progress, right? This is just saying, suppose you start at the center of the circle, so your measure of progress is 0. At every point in time, you increase the progress by some. You get more progress. You move outwards. You're always moving outwards. And, well, I haven't proved this, but you're not doing a step and then a half step and a quarter step and an eighth step, right? You have to prove that you actually can manage to get there. Then together, you're going to eventually get to the quarter mark, right? Everybody buy that? This is how we prove that we get to the quarter mark.
Can you explain that maybe in a different way?
All right.
Is this generic? Is this generic thing, or this is like you just call like?
So it is generic, but I've turned it around. All right. So suppose that you have a number on your phone that changes. All right. And suppose that you start with the number being 0. And at every point in time, the number on your phone increases. And when I say increases, it doesn't just increase by a smaller and smaller amount, right? It really increases. At each point in time, it increases by something. Would you believe that at some point, the number has to reach a quarter?
Yes. Some point, though.
Some point, right? Am I telling you anything about how long it takes?
Nope.
No. We're not doing running time here, right? We didn't tell you whether you'll make it home for dinner when you're in this lake. All we're saying is that eventually you will solve the problem. So that's all I'm saying here. So this is having your measure of progress go down. So it's slightly different. Here's the different thing. You start with your phone here when you're at home starting. You start with a number on your phone that's it could be a really, really big number, but it's finite, right? So your initial number is not infinite, right? Here we're saying at every point in time, that number decreases by something substantial like 1, right? Can you guarantee me that your number will eventually get to 0?
Decreasing or increasing?
No, in this case, it's decreasing. Here we're going from 79 to 75, right?
Eventually.
Yeah, eventually it'll get to 0, right?
Right.
That's all I'm saying here.
Oh, so this is like a religious rule of thumb thing.
It's not even a rule of thumb. It's a religious fact.
Okay.
Right? Religious fact. It's if you start with a finite number on your phone, and that number clicks down each time step by at least 1, then at some point, you might be dead already. I'm not saying it won't take a long time, but eventually it will reach 0.
Right. So
Right?
this is just like a generic step that we're talking right now, like outer surface. Okay.
Yeah.
Got it.
Right. We need to understand this generically so we can apply it. Right. The way we apply it to the lake problem is kind of the flip. I start at 0 and I keep going out, so eventually I'll get to quarter.
Right.
Right?
Yep.
That's how I know I get to a quarter, right? And another thing we prove, right? So this proves you'll eventually get to a quarter, and this proves that if you get to a quarter, you'll exit, right? So that proves our algorithm, the loop will eventually exit, right? So this proves to us that our algorithm will eventually get to the quarter mark, right? Everybody good with that?
And then we exit.
Hmm?
Sorry, and then we exit, right?
Then we exit. All right, so now we're moving on to the last phase of the algorithm, right? Now we know that we've exited, and when we exit, we keep having the loop invariant, right? Because the loop invariant is true until we exit. So as soon as we exit, it's true. And we prove that if the exit condition is true and the loop invariant is true, then we can swim for it, and we'll get the post condition. So hence we got the post condition.
But,
And then, yeah,
I was just gonna say that green arrow in the middle, like we still
Yeah.
have to show some kind of
prove that.
yes, right? Yeah.
Yes,
Okay.
that's what this circle is. What this circle says is that in your algorithm, when you're writing up your test, one of the things that you have to prove is that if the exit condition is true and the loop invariant is true, then you can do some code to get your post condition. Right?
Got it.
This circle you need to achieve. And what I'm saying is if you have achieved this circle, then, well, I'm saying, well, your program will exit, the loop invariant will be true, and then you've done this circle, and hence we'll get the post condition, right? So the bottom, we're going the wrong direction, right? So what am I saying? I'm saying if you can do all of these things, then you have an algorithm, right? That's what I'm claiming. That's my religion. My religion doesn't tell you how to do each of these pieces. The religion says, if you've done all of these pieces, then I call that an algorithm. Right? So what do you have to do on a test? Well, you don't have to worry about this entire algorithm. All you have to do is each of these pieces. You do each of these pieces, and then you hand in your test. Right?
Wait,
Does that make sense?
Can I ask?
Yeah.
Sorry. Just a quick thought. Like, is it possible to have an exit condition equal to the post condition?
Oh, I have slides about that. So people are often tempted to do that, right? And that makes this step trivial, right? Because if the exit condition is true, then obviously the post condition is true. Why? Because they're the same, right?
And you just return, and that's it.
And you just return, and that's it. But why is that bad to do? Well, because this is a step that I require you to do on your test, and you've just made it silly. While this step I don't often require you to do. I only require you to do it if you can't do it, right? I want you to check that you can do it. So how do you do it? What do you have to do here? You have to prove if my measure of progress gets sufficiently small, then I'm guaranteed to exit, right? So now the exit condition's equaling the post condition. So now you've just moved all the work here. You have to prove that if my measure gets sufficiently small, then I have my post condition, right? And that's not good. So what we did on the lake example, we had my so I was going to say something that was wrong. So let's not say that, right? I mean, for example, you could say, let's say we were doing the more complex thing where you're spiraling all the way, right? Then you could have my exit condition be that I'm at the shore and the monster's there, and the monster's not there. Well, then that's too much to prove. So instead, let's have the exit condition to be that I'm at the shore, and my measure of progress is how far I'm from shore. So if I make enough progress, then I'm guaranteed to get to shore, right? And then you come over to this step, which says, if I've made it to shore and I've made enough progress, then then I'm at shore, and the monster's not there, right? So here that makes this step pretty easy, right? We want this step to be easy. We want that if you make enough progress, then you'll exit, right? And if this step's not easy, what you need to do on your test is you need to think, in my algorithm, is this step easy? And if it's easy, then ironically, you don't have to do it, right? And if it's hard, then I'm going to nail you for it, right? Does that make sense? Now, when I just let me say one more thing. When I say you don't have to do it, well, somewhat you do have to do it, because I'm going to ask you for a running time. And if you haven't done this, then you don't know how to do running time, right? Running time assures that when my measure of progress gets to 0, I'm bound to exit.
So what is the running time of the late problem?
Oh, I have no idea.
Okay.
Absolutely no idea. Why? Because in fact, the truth, if you want my absolute truth of my most recent panic, is where is it? Here, right? So the way you usually do running time is, suppose your measure of progress is going down, right? It could go up or go down. It doesn't matter. You just subtract to get the other one, right? So if my input is, in objects, and I start with the measure of progress in, and each time my measure goes down by 1, then I know the time to get here is n, right? I just take the amount of progress, I take the difference between this and this, is how much progress I need to make, and I divide it by the amount of progress I make every time step, and that tells me the number of time steps I need, right?
That makes sense.
Right, but in this algorithm, it is true that the closer I get to the quarter mark, the slower I make progress, right? In fact, when you get to the quarter mark, you stop making progress, right? So have I actually proved that, that as you spiral, right? As you spiral closer and closer to the quarter mark, your progress out gets less and less. So I haven't actually proved you make it to the quarter mark. But let's just move the definition of exit condition. Let's move it that choose some 0.0001 and have the exit condition mean that I'm 0.001 away from the quarter mark, right? And then what is my step? My step is always at least 0.001 because I'm still that far away, right? And so I know I'm actually making a solid progress. And so that assures me that I get to be 0.001 away from a quarter, right? And then when I do this step, I have to say, well, it's okay that I'm not at the quarter. I'm 0.001 away from the quarter, and that won't affect my swimming for it, right? But I kind of slipped that under the rug not to make your life harder.